Hey guys, good morning, good afternoon, good evening, wherever you are on the planet. Mike Aubrey, and then as always, my partner here in crime, Princess Aaliyah Adolfi. Hello. And guys, today we're talking about composite materials. And so with us today, we actually have a composite material business that's chatting with us. So Alan Taylor, I want to introduce you to him. He's the founder and president of Rapid Composites. And so they're a provider of engineering services, skills, training, expertise, resources in this specific area. And so, of course, what that means for us in the UAV world is, lighter, stronger materials. So Alan, thanks so much for taking the time to be with us today. We really appreciate you coming out, hanging out with us. So, Alan, just kind of how these things generally work is we have a series of people that are just kind of here from around the world. They vary from Europe and South Africa and North America. And what they'll typically do is, as you kind of show off the stuff that you were thinking to run through, they'll throw questions our way. It's kind of whenever there's kind of some natural breaks in the presentation and whatnot, we can kind of get this more of a dialogue. It's pretty well you choose your own adventure and how you go, but yeah, definitely feel comfortable to kind of go off script if you want to. I mean, we're really interested in this stuff, and we're really appreciative of your time.
Thank you very much for the introduction there, and I sincerely appreciate the opportunity here to present to everybody, and I'm very pleased to be a part of this this great cause, and anything we can do to help and offer support and direction and perhaps a little bit of guidance along the way. With our knowledge and experience, we are very happy to do so. So definitely feel free to compile questions as you have them along the way, and I'll be happy to answer them, or one of our people will get back to you in a timely manner if we run out of time today. I think what I'm going to probably start with initially, just so everybody gets an understanding of our background and what all we do. First, I'm going to go through our e-brochure just real quickly, just to give everyone an idea of our background and our experience and our knowledge base and a bit of where it comes from. And just the gist of it is, I'm the president and founder of Rapid Composites, and we've been around for 15 years now, since 1999. And one thing that you will see as a common denominator amongst the bulk of our clients is that we're usually doing something out of composite materials. We specialize in high-speed processing techniques above and beyond anything else when it comes to composites. So we've worked with all of the age-old processes, which I'm sure many of you are familiar with, and for those of you who maybe aren't familiar with them, I'm going to be giving an overview of kind of a broad overview of what the industry has right now, what's available in the industry. So all the different processes and material categories, material science categories of relevance in the industry, I'm going to try to cover as much as I can, or attempt to today. But the gist of it is, our focus has been over the years really getting to the high-speed processing. So for those of you that are familiar with wet layup processes and autoclave methods and things like that, we consider those slow. So everything that we do in general, all the products that we make, categorically, we produce in around 11 minutes or less. Some of the product we make in as little as 45 seconds in multiple quantities. So just give you an example of what we're capable of doing here in-house. We do industrial design, electromechanical engineering. As you can see my cursor here as I move along. Rapid prototyping. We cut our own tools. We operate our own tools. This is a trimmed and painted component that goes to this mobile SATCOM device, and this was, at the time, the smallest mobile man-portable SATCOM system in the world. So we literally go from napkin sketch to full production in-house. We have, sorry, my mouse here is a little sensitive. This is a pod that we did for the Predator drone years ago. It's a 4-foot pod, to give you an idea. We have in-house industrial design, electromechanical engineering. We design and manufacture the lightest rack mount transit cases in the world, flyaway cases. We're even working on a new gun case right now. It'll be 30% lighter than anything on the market. The bulk of the product that we make is for military applications. A lot of times it's for special operations type stuff. Some of it is, I would tell you, most of it's domestic for here in the U.S., but some of it is done for international customers as well. We also have in-house electrical engineering capability. We do firmware, BIOS, and software. We have some testing capability, although over the years we've been trying to get out of the testing side of the business as much as possible, since most of our customers want third-party testing anyway. Now, manufacturing. As I mentioned, we focus on really high-speed processes, and these are some pictures of a part of our manufacturing operation. A lot of our equipment is very vertical. It's very tall. We operate, we do a lot of our composite molding, and I'm going to get into more detail on this, in vertical press systems. So typically our stuff is matched metal tooling, core cavity tooling. The parts tend to be highly accurate. They're produced under a tremendous amount of pressure, and we work with, if you were to lump composite structures into two main categories, they predominantly fall under either a thermoset category or a thermoplastic category, and we work with both. But we, again, focus on the high-speed versions of those processing techniques and materials. We do in-house rapid prototyping. We spend a tremendous amount of energy on material science and really determining from the get-go what the best material selection will be for a particular project and process. This page right here, and we can get you, anybody who doesn't have a copy of this, e-brochure, but all of these thermoplastics you see along the bottom of this page here on page 18 are standard polymers that we work with in the thermoplastic stuff. And that'll become more relevant through my presentation. I'll explain in more detail. We also do EMI and RFI shielding in some extremely unique ways. Right here on page 20, these are all metals that we co-laminate into structures. So for EMI and RFI shielding, and we're going to explain how a lot of this stuff is done as well, because you know, in the UAV world, this is becoming more and more relevant, being able to strategically shield components that you want shielded versus you know, ones that you might want in a dielectric material or a radiolucent material for, you know, radomes or antennas, that kind of thing. We also work with thermally conductive materials. So on page 21 here, it's kind of the start of it. We work with a lot of pitch fiber materials, and we create some extremely unique structures. So we do everything from bonded fin designs with pitch fiber, which is a crystalline carbon material. We have pitch fiber, it's up to 900 watts per meter K that we work with. So it's more than twice the conductivity of copper. It's about half the density of aluminum. And therefore, it's about half the weight of aluminum. And what pitch fiber, a lot of people don't understand about pitch fiber, that really sets it apart is even when pitch fiber is in the exact same conductivity as aluminum, for instance, which is 200 watts per meter K, copper is 400 watts per meter K, about twice that of aluminum. Pitch fiber, its dissipative properties are about 4x that of aluminum. So therefore, it operates more efficiently than aluminum. And a good way to think about it, and this may become a very relevant subject for some of you that are dealing with significant heat issues, like with speed controls or motors, that kind of thing. And pitch fiber, the way to think about it is like a frying skillet. So we've all fried eggs before, and if you were to use an iron frying skillet, for instance, and you take it off the stove, off of a burner, it wants to store that heat energy for a very long time. Whereas you know, an aluminum skillet will store that energy less for a lesser amount of time. pitch fiber will do about 4x better than that aluminum will. So it's quite a bit more efficient. So now we work with a lot of conductive materials and superconductive materials, as you can see with pitch fiber, and then also we co-laminate metals in ways that are quite unique, where you can actually solder to the structures, as I showed you with the expanded metal. We also conversely work with a lot of non-conductive materials. So we have materials like the ones you see here, in some cases like the e-glass polypropylene right here. It's got a dielectric constant of 2.5 or less. So it's a very good durable material that we can mold extremely fast for radomes and belly pods and antenna caps and that kind of thing. And in fact, in some cases, we can actually combine it and insert mold it into other materials that are more conductive. So for instance, we might shield around the perimeter and then have just one little spot that we plug into the mold that is non-conductive and radiolucent. So page 25 here, this talks about rapid cure composites. Now, this primarily is, now these are going to be thermoset materials. Everything I showed you up until now has been thermoplastic. But, and I'm going to get into more details about this. And a lot of people are familiar with SMC type materials, which stands for sheet molding compound. TMC is thick molding compound. BMC is bulk molding compound. And EMC is engineered molding compound. So the differences are fairly significant, but there is a common denominator amongst all of them in that they're quasi-isotropic and they're discontinuous. So they're basically a 3D oriented fiber. And right here at the bottom left corner of page 25, you'll see a diagram here that shows how the material is chopped. And the chopper process, it's actually explained in this diagram. There's quite a bit of information you can draw from that. The chopper, the helix in the blades, controls the orientation of the fiber as it falls. The distance between the helix of those blades controls the length of the fiber. So those two main parameters are controlled right up in this top portion of the apparatus. And as it falls onto a carrier film that is rolling around here from the front. A resin paste is applied to that carrier, that mylar film. So basically the fiber falls to that surface, sticks to the resin, it gets carried through another carrier film that gets wrapped around with more resin paste, and then it goes through a series of staggered rollers. And those rollers basically are causing kind of a chafing motion to help impregnate the fiber and compress it down to a 2 or 3 or 4 millimeter thickness that then gets re-rolled at the end of the machine. So understanding that process of how that works, and that's kind of the simplistic overview of it, is very critical to understanding why the fiber is what it is. It's basically in a 2D form. Quasi-isotropic materials have more torsional and tensile stability than you will get out of a typical 2D 2x2 type fabric material. So this is a 3D oriented fiber. So even when it's in a 2D form, it is 3D. So it's very structural. And then imagine if you put a part into a 3D form, you do a highly contoured hull component, let's say for a UAV or a fuselage component, it's going to be massively more torsionally stable than you're going to get out of a typical 2D 3K kind of fiber. A woven type fiber. So another thing that we do a lot of is compounding and hybridization. So this is an example of actually a patented version of a material. Well, it's actually a combination of materials here. We've got polycarbonate on the outside surfaces, carbon fiber. There's PET, polyester thermoplastic glass tape that's pre-impregnated unidirectional glass tape. And then there's PETG, which is polyester thermoplastic with glycol, that actually flows like water. And there's some significant things that are occurring in this this compound solution that we have here, this hybrid pre-consolidated panel. Basically, we're creating a pressure intensifier with a sacrificial material, which happens to be PETG in this case. All of these materials are reasonably compatible in the form that we're putting them in. And it creates pressure intensification from the inside out. So we get Class A surfaces on both sides. And that, up until this process, was pretty much unheard of in the thermoplastic industry. It's been a big problem for many years. Most thermoplastic components in the industry have been dedicated to behind-the-scenes components, things that you'll see behind the bumper of a vehicle. A lot of times are parts that you would just never come in contact with unless a vehicle was in a wreck or something like that. We do a lot of continuous fiber molding. That's going to be another thing that you'll hear a good bit about in the follow-on presentation I'll be going through. We work with both continuous and discontinuous materials, and we work with materials that are pre-impregnated with thermoset resins, but also with thermoplastic resins. And we also work with them in drapable fabric form in both categories, both thermoset and thermoplastic, and also in a pre-consolidated form, where they're pre-consolidated into a continuous thickness. So for instance, we have materials that can be consolidated at 1 millimeter, 2 millimeter, even quarter millimeter thicknesses in quarter millimeter increments. In fact, up to 6, 8 millimeters even in thickness that can be heated to their melt point, so they become like a wet, drapable like a wet towel, hot stamped and simultaneously cooled inside a matched metal tool in a vertical press. So, to give you an idea, that process typically, even in some of the largest components that we make, can be in less than 5 minutes, pretty much categorically, I could tell you. And that's even when you're running polymers like PEEK, polyether ether ketone, that's very high temperature and requires about a 780-degree Fahrenheit melt point. So, so it's a very fast process. There's limitations of it, and one of them is that it wants to be typically a continuous thickness. And we'll get into more detail on that stuff in a bit. So just some examples. Now, we not only do we go from napkin sketch to full production, but in-house, we have all those engineering services I explained. We do rapid prototyping. We also cut our own tooling. We have a massive machining capability in-house. We can machine 10 by 5 feet by 2 feet in-house. We also operate our own tools. We design our own press systems, our own shuttle systems, carrier systems, and heater systems. This is an example of one right here that we did. That's me actually standing next to the machine, so it'll give you an idea of the scale of the machine. And I'm 6'4". So this machine is basically about 32 feet long. The press sits on the back side. And we developed it, oops, I'm sorry. We developed it for the floorboards for the Lamborghini Gallardo and the Audi R8. Our Lamborghini is a customer of ours. We work with their ACSL, Advanced Composite Structures Laboratory, and we've been the behind-the-scenes partner on their thermoplastic stuff that they're going to be putting on their next-gen vehicles. Their floorboards at the time when they came to us for the Gallardo and the R8, which is basically the same car, looks different externally, but internally the chassis and drivetrain is identical amongst those two platforms. And the floorboards were being produced in 2.5 hours with their fastest vendor, and that was using an autoclave approach. We took it with this system, with this shuttle system and heater system and press configuration, we took it from 2.5 hours to 2.2 minutes per part. So, so it's a very fast process. This will give you an idea of the typical kinds of machining centers that we work with right here, but big build envelopes and accurate and big build envelopes. And we're doing a lot of times matched metal tooling. Most cases, it's matched metal tooling. I would tell you about 80% of the time when we're talking about mid-range volumes. And the way I describe mid-range volumes would be anywhere from about a 200 unit per annum build to 5,000 unit build. And assuming that there's adequate draft on the molds, we can typically get 5,000 shots out of a single aluminum tool set, assuming they are plated. When we have to go to higher temp materials, instead of running nylons or vinyl esters in the thermoset world, go to something like PEEK or LCP, liquid crystal polymer, which are real high temp materials, we then have to go to steel molds. And the steel molds can typically, again, assuming you have adequate draft, if you do P20 with S7 inserts, let's say, 50,000 shots to 250,000 shots is possible out of those tools. So the volume can go up significantly. So sorry, my mouse is extremely sensitive here. Give you some examples of the types of products that we do currently. These are all products that we've produced in-house, and it's only about 10% of what we've done over the years. It's just what I'm allowed to show. So this is a 2U rack mount system that we did for a defense company. We do pin-fin heatsink solutions for ATR chassis, docking stations, transit cases. This is a bonded pitch fiber solution right here, bonded fin design. This is a head unit for a robot. This is a positioner system for a 1.2 meter reflector. It's a gimbaled motorized SATCOM system, a KU band SATCOM system. We work on everything from LWS or LWTS, lightweight thermal weapons systems, to handheld computers. This is that SATCOM system you saw in the beginning. These are pitch fiber heat sinks right here we did for a machine gun that performs substantially better than an aluminum heat sink. And we've done an aluminum and a copper version of that. We also we do MRT type systems, mobile data type terminals for vehicles, including Humvees. This is a handheld device we produce, tablet computers, FLIR binocular displays, the cameras that give a 360-degree view around the Stryker, the Bradley, and the M1. Basically, every one of those armored vehicles gets this camera system that we designed. It's a thermal system for. It's actually more a safety system and a security system than it is anything else. We do composite structures for weaponry, all sorts of different kinds of handheld devices, tablet computers, even some commercial stuff. There's an eyelid retractor for ophthalmologists. This is a fiber optic system right here. It's an all composite structure with an aluminum chassis that gets bonded into it. We make the best attaché case in the world, we believe anyway. This is for the Lamborghini Aventador, in fact, and there's cartridge bearings in the hinges of this and gas strut openers.
All right, Alan, I'm going to have to get myself one of those.
Yeah. There is no purpose in the world for this, no practical or reasonable purpose for this product in the world, but it's a good showpiece for us to just show what we're capable of. Basically, every component on this product, except for the leather goods inside, we did in-house. So,
I think I could think of a few things I can use it for.
They're pretty pricey. We're actually more inclined these days to not make them because they're so expensive for us to produce. Every fiber on this product has to be in the perfect place, and that's one of the hardest things to do with it. So the yield on production is not so good on this product. So we've done earbuds and headsets and putters and a pretty wide array of products, as you can see, defibrillator. Even grills. So we've worked on consumer products in the past. We do membrane keypad design. We also, one of our big things is, devil's in the details, right? And our objective is always to scrutinize every single component down to the last screw on the products that we manufacture. So we want our latch mechanisms to be the best and the most robust in the industry. We want them to be as ergonomic as possible and as user-friendly as possible. So our objective is always to make the best of the best of the best. So you will see that across the board with the types of products that we do. Our cam latch mechanisms are simple, they're rugged, they're ergonomic. There's no pinch points. So we think through those types of things, and there's nothing worse when you've got a great product overall, but the human interface portion of it's not so good. And what we've found in the past is, we do things like that for law enforcement. We develop product, especially things like handheld devices or mounting solutions, things that are, have a high degree of human interface with our customers. If they're not ergonomic and comfortable and they're not easy for them to operate, they'll stop using them. And that can mean, putting them in a dangerous situation if they're in law enforcement or military. So our focus is always to take those types of things into consideration in the products that we develop. So, here's some more images just to give you an idea of the extent that we go to of developing equipment. These two images right here to the left are very large shuttling. They're shuttling heater systems on the front sides of very large presses, and this is the back side in the image here just to the right. These big panels you see right here are the control systems. They stand about 6.5 feet tall. There's a 12.1-inch touchscreen just so you can kind of scale it. And those control panels control nothing but the heated platens in the press. These presses, there's two of them side by side. We've sold them to two separate customers. And these presses are 600. They operate on 600 amps at 480 volts, to give you an idea. So they're extremely powerful, electrically intensive machines, but they operate, very, very fast. So the amount of energy that's expended per part is actually quite low. This happens to be at the end of our brochure here, a new tricopter UAS that Princess Aliyah and Ron got to see at the AUVSI show. Some of you might have had the opportunity to see. That's amphibious, and we're in the process of tooling this right now, and we'll be capable of producing this 32-inch fuselage that's highly contoured, it's highly faceted, in a single-shot tool, family tool, in about 10 minutes, to give you an idea. So we're going to be using quasi-isotropic, discontinuous 3D fiber for the production of that fuselage. So I'm going to definitely spend a little bit of time going over that process a bit more so everybody understands it, and offer our help for this cost. So I'm going to move on to go ahead and bring up that other presentation, Matt. I'm going to move on to the next presentation here, and I have a feeling this is going to bring up a lot of questions. I'm going to try to work the beginning of this for a lot of you is going to be the processes you are most familiar with, and you might even be doing right now. So
Alan, so as you do your presentation, can we take questions while you're, Mike, what's your suggestion on that?
If you like, you can either do that or we can save them to the end. The only problem is that we've got, how many slides do we have on it now, Matt?
65.
Yeah, I think it's 65 or 65.
Yeah, I don't think we're going to go through all 65 slides.
Yeah, so I can blow through a lot of them pretty quick. I'd maybe,
halfway through right now.
Okay.
Halfway through. So.
Yeah. So I'll be happy to take any quick. Why don't we take quick questions as I go through the presentation? Then at the end, I'm happy to stay online as long as I need to.
Okay.
Questions. Does that make sense?
Yeah, I think that's good. Yeah. All right.
I can certainly jump back to anything in the presentation because, see, I think a lot of what we're going to have in the beginning of this, many of the listeners are going to be familiar with, and I apologize to any of you for any time I waste on subject matter that you already know, but just so everybody gets a global understanding of the industry and what's out there. And it's really, it kind of makes the argument, it leads into why I'm going to suggest what I'm going to suggest towards the end of the presentation, why you should go a different direction in many instances. And I'll explain the alternatives to these processes along the way as well. So, this is very much a work in process, by the way. We have pulled the information together from all over the place. A lot of the data is stuff that we developed here and created here, and it's processes we do here. And then in some cases, it's stuff that we pulled together from elsewhere that we just know, some of you are going to be familiar with, or it might be a path you would go down otherwise. So, so let me jump to number one process in the industry right now. The most ancient technology, if you can call it that, in the composite business is hand layup and wet layup type approaches. So this approach is a very messy approach. And you can see in the advantages there, it's capable of molding large structures and the tooling is inexpensive. Disadvantages are poor tolerances, non-uniformal thicknesses, labor-intensive post-processing, and that really is just, those are just the high-level disadvantages, I can tell you. There's more to it than that. There's a lot of carcinogens. There's a lot of really bad VOCs that you have to work with. There's a tremendous amount of particulates. It's messy. I can tell you the list goes on and on, but basically the way to understand this process is it's just like you see here. It was developed for the boat building industry, for developing hulls and manufacturing hulls for boats, and it has grown into an industry now that where this technology is applied to fuselage structures on aircraft in many cases. It's utilized in the race car industry, not efficiently, and it's really not the best approach, but people that are doing sometimes 1 or 2 or 3 of something still use this approach. And really the only arguable advantage to it, I would have to say, is the low-cost tooling and the fact that you can make very big tooling. You can make tooling out of wood if you wanted to. So from if you're doing the very first of something, it might make a little bit of sense, but I would argue you'd waste so much time doing it that you would still be better off spending a few extra dollars to, go down a more expensive but more efficient approach than this. So basically, this approach is just you apply fiber, resin, until you build up your desired thickness. In most instances, they'll vacuum bag it. There are people that still do not do that, and those people will have even worse variation in thickness. If you did a boat hull like the one these people are standing in, they probably have a variation in thickness of 1 inch from one end to the other, to give you an idea. At least 1 inch, possibly even 2 inches. So imagine you end up with a lot of resin richness or resin deficiency, and neither of which is good. So very messy process, and there's a lot of diagrams and examples I gave, and I'm just going to kind of blow through these here of different ways this approach is done. So you'll see it's all titled the same way at the top of the page. Here's images right here going from from left to right, where they're pouring resin onto the fiber. Sorry, that sensitive mouse again. I gotta be careful. They're taking an applicator and they're spreading the resin out, nice and evenly across the carbon fiber here. This is another image right here of a UAV component, in fact, that's being made that way. And then this is an image right here where they're vacuum bagging it, and this is the double-sided adhesive that's used for the vacuum bagging process. So it's a very messy, lot of expendables. There's a lot of stuff that goes in the landfill. This is absolutely the antithesis to anything environmental, I can tell you. There's nothing environmental about this process. Again, more images here to just show what a labor-intensive process this is. I mean, there's a massive amount of time that goes into the setup and just laying out all your expendables, applying the materials, creating a custom vacuum bag, putting a vacuum valve in this, drawing 1 atmosphere of pressure. The tools are extremely inaccurate typically, everything's very messy. And when you're at the end of the day, this is the kind of part that you end up with a lot of flash around the edges that requires, at a bare minimum, it to be routed, to be trimmed, which is very messy and sloppy, or to be cut on a machining center. And in most cases, people are not using the proper machining centers or not using graphite machining centers. So they produce a tremendous amount of particulates that are lung depleters. So these are very, these materials are electrically charged particles, and they'll float around your shop environment basically forever unless you hose it down with a fire hose. So it's a very nasty process in general. The next process that's number 2 most popular in the industry, and this is a step up from what you just saw. I should have, sorry, I should go back to this just for 1 second. There's something I forgot to explain. When people are typically doing a hand layup or wet layup process, and they vacuum bag it, they're pulling 1 atmosphere of pressure on that bag. So 1 atmosphere is equal to 14.65 psi. So it's very, very low pressure. And some cases, people are allowing this to air cure and just at ambient room temperature. And it can take, depending on the resin system we're talking about, the specific epoxy that we're talking about, the amount of catalyst that's being used, a lot of factors in it. But, it can be anywhere from days to weeks to get that, your first part out of that mold. And not only that, because of the inaccuracy, the parts are, they're going to be very difficult to trim and post-process afterwards. Now, if the parts are small enough, a lot of people are taking these molds in the vacuum bag systems and putting them into an oven, and they're still only at 1 atmosphere of pressure, and but they're causing the resin to kick faster, obviously, by applying more heat. So, you can get the parts a little faster in as little as maybe 2.5, 3 hours per part, but you still require that trim. So, you could spend, on a very complex part, you could spend all day to get 1 part. So, and this is what is being done 80% of the time around the world. The number 2 process is an autoclave approach, where sometimes they will use a more accurate tooling method. They might make a single-sided aluminum cavity mold, and then apply the materials to the inside of the cavity mold in a very similar fashion to what you saw in the wet layup, except that they're not brushing on the resin. Or spraying the resin. They a lot of times they'll apply it through a vacuum type approach, or they will use pre-impregnated fabric materials, and that's really the most popular with this type of approach. It still gets vacuum bagged, and the vacuum bagging process outside the autoclave is done really to massage everything into place. It's still only 1 atmosphere of pressure on the outside of the autoclave, but once it goes into the autoclave, you can apply about 10 atmosphere of pressure. So let's just say about 150 psi in total. So it's 10 times, it's literally 10 times the pressure on the part. So your thicknesses tend to be more uniformal. But because it is still low pressure comparatively to the other processes I'm going to get into later, you still have some reasonably significant variation in thickness. So just to put it in contrast, the variation in thickness on, let's say, a fender for a Ferrari, and Ferrari is very good at doing this process. We know them, and they do an extraordinarily good job at it. A fender on a very high-end vehicle of theirs might have a variation in thickness of 20 or 30 thousandths of an inch from one end to the other. So, about anywhere from 0.5 millimeter to 3/4 millimeter approximately. So that's still not accurate enough for some of our customers. So this approach is often not acceptable for us even. It's also a slow process. So you still have extremely slow cycle times with this. You could spend an hour or 2 just laying up the material into the molds, vacuum bagging it, putting your intensifier in it. Usually these molds will utilize a silicone intensifier or some sort of a bladder type system. They'll get vacuum bagged. You'll load your valve. You will pull vacuum. You'll kind of massage everything in place. You'll put it in the autoclave, close the autoclave, apply 10 atmosphere to it. You'll cycle sometimes 2, 3, 4 times, depending on the resin system you're doing, different temperatures. You'll have a curve that you're going to follow. You'll depressure the autoclave after that process has transpired. You'll cut the cut the bag, throw away the bag, save the valve, pull the part, load the part into a machining center, and basically do your post-process trim and drill operations. So everything's said and done. If you were Ferrari or Lamborghini and you were really proficient at this and you made the same part every day, all day long, you maybe could get through that process in about 2.5, 3 hours. But that doesn't, again, still doesn't include that trim process I described. So, it's very tedious and requires a lot of handwork, and you can only make one part. You have to have if you want to make multiple parts, you have to have multiple tools through this process in that same time frame. So there's a lot of diagrams in here that explain, kind of the process to it. And in the next categories, I'm going to, try to move on to, because we're running out of time here, as quick as I can. And sorry if any of this seems a little disjointed. It's just a lot of information to try to cover, and it's important to understand these things before you, try to understand why I would suggest you go to a more expensive tooling approach over.
Alan, I think we'll definitely have to do a part 2, because this is really great information, and I think having a part 2 to more advanced would be a good follow-up webinar for you to finish up the slides that you did prepare.
Sure. So, the next processes I'll explain is RTM and VARDM. Okay, and these two processes, RTM has been around a while. That's the third most popular approach in the composites industry as a whole. It stands for resin transfer molding, and VARDM is a kind of new spin on RTM, and that is vacuum-assisted resin transfer molding. And that's becoming more and more popular. That is what the high-end auto manufacturers, a lot of the UAV manufacturers, the AeroVironment types, a lot of the bigger companies out there are utilizing the VARDM approach. And basically, this diagram, this page right here, I thought would be really helpful to put on there, because it describes, literally each row here describes the different processes. So, and I'm not going to go through these in detail, but basically the gist of it is you're taking a dry fiber material, loading it. Sometimes you'll harden it, you'll form it on a preformed die, and then you'll load it into a mold. And in some cases, it'll be a matched metal mold in a very low pressure press. Okay. It doesn't have to be a press, however. There's different ways, like VARDM does not require a press at all. You can actually do everything with vacuum bagging if you wanted to, and you can augment the process and improve your cycle times by either using an oven with that process, or use a heated autoclave, which is an even better approach where you get better pressure, and that's what the high-end auto manufacturers would do. So, so RTM is typically with matched metal tools. VARDM doesn't have to be with matched metal tools, but it could be. There's also an RTM light process here, and then there's a compression RTM process as well. So you can, on your own, if you want, go through these different processes, and certainly ask questions along the way if you like. But I thought this, would be a kind of helpful chart to just explain, the main approaches to RTM. And there's even hybrids of all of this, I could tell you. So there's so much to what I'm trying to describe right now in 1 hour. It's not funny. So again, there's a lot of other diagrams in here that I included to just explain different embodiments and variations of how RTM and VARDM works, and then also how you would layer the materials, and there's a breakdown of structurally how you would put together a mold and how you would seal it and shut it off. So This right here is a mobile unit. So, if you're doing a really large component, this is sorry, that mouse again, mind of its own. This mobile unit right here is a pretty neat system, and it allows you to move it around in your shop and go from while you're demolding one component, you could be going to another mold and basically working another mold while another's being demolded. So, and again, this explains the process of how it works. I wanted to include also some, just quick images in here that I can explain to you, to show examples of, on the right side there is a very large windmill turbine blade tool for doing a single, rotor blade. And, that gives you an idea just how big you can go with an RTM or Barden approach. And, there are huge molds these days where they're applying these approaches. On the left side is the new monocoque for the McLaren MP4, and that is the entire driver and passenger tub. It's made up of, as you can see, multiple components that are all joined together in a single RTM process, and it's a reasonably fast process. They are making one of these tubs in about 4 hours now with the aluminum inserts and all of the bulkhead mounting and so on for the engine and the suspension, the aluminum primary crash structures. So it's a reasonably efficient process, although still quite messy, and there's a lot of expendables that go in the trash and end up in a landfill for 10 million years. So that's one of the bad things about all of these processes we've covered so far. Another popular process, I won't spend too much time on this, is pultrusion. A lot of the tubular structures you see for booms that might get used on UAVs. In fact, we have pultruded booms on our vertical takeoff UAV ourselves. Basically, it is a process where you have, this diagram explains it quite elegantly. These are creels right here of glass fiber, and those creels get pulled in close proximity to one another through an impregnator here that impregnates it with resin. Usually it's epoxy, sometimes it's vinyl ester, and then as it pulls it from the very end of this machine here, it goes through a forming die and basically forms the structure into a linear shape that then gets chopped off. And again, I won't spend too much time on it, but sorry, there we go. So this is a typical die system, and they even make die systems like this where it actually impregnates as it goes through that process, so there's not a separate resin bath that actually occurs in the die. They can do spirals and spring-type designs like this, helix shapes, and then here's also pultruded tubes, which are pretty typical. And we gotta adjust this mouse, it's terrible. It is terrible. If I breathe, it moves. You know what? Yes, actually, that's what it is. Sorry, little technical difficulty here. Let's see if I can.
9 minutes left.
There we go. That's much better. Okay, perfect. So the next process here is filament winding. So pressure vessels, and again, a lot of diagrams in here that explain how that's done. Some big images of big parts that are made with that process, and smaller parts, carbon, glass. Virtually every kind of material has been, run in this process for doing pressure vessels, hydrogen tanks, things like that. So another, it's kind of a hybrid between the filament winding process and some of the latest, greatest robotics technologies is the robotic tape placement processing methods. And this is a 6-axis robot that is doing a highly contoured, as you can see, tubular structure, and it's applying tape. And that's carbon tape, and that tape can be impregnated with thermosets. So it can be epoxy, it could be vinyl ester, it could be something that you ultimately cure by heating in an oven, vacuum bagging, autoclaving the part after it's been applied to a mandrel. You could even apply it to a sacrificial mandrel that you dissolve out of the center. You could also use smart tooling. There are smart tooling systems that you can heat up, pull vacuum on, extract a shaped tube out of the center of this thing, and then reshape it to a mold. And they call that smart tooling technology. So that again could, might be a part B or part C, video conference we might want to do in the future. But that gets even more complicated than this. But basically, these systems can also do thermoplastics. So right now it's applying a thermoset, but you could do thermoplastics, and some of these machines are capable of being equipped with ultrasonic, basically where they ultrasonically fuse the tape layers together in thermoplastic form, like PEEK or PPS, polyphenylene sulfide, or sometimes they will also use radiant heat, or UV heat for fusing one layer to the other. So it's a pretty sophisticated process, but not fast. Of all the high-tech processes out there, this is probably one of the slowest. And here's a bunch of other examples of different, yes?
Can we finish the robotic tape placement processing technique? Because we're at the end of our time.
Running out of time, yep.
So we can just open it up for questions. But I think that you've done such a fantastic job. I think this is very, very informative. And I'm sure we want a follow-up to the rest of what you've created for the presentation as a part 2 to your composite materials.
Sure.
Can you go back to that slide you were just at?
This one?
Yes. Yeah, if you can kind of talk a little bit more about this one.
Okay, so these are still just, these are additional head units, very similar to what you see on the end of this robot. These are just bigger ones. So these are all rotating mandrels for the most part. Well, take that back. This image right here is a rotating mandrel. So you can imagine that could be a wing structure. Right here, this is right on a table. So it's actually doing a tape structure where you're controlling the orientation of the fiber. This is where it's doing a contoured shell on a mold that is it's angled at about 70 degrees. And then this is just a real up close look at what's going on inside the head of one of these tape dispensing units. And like I say, you can do this with you can apply the heat in many different ways. You can do it post-process outside of the mold, outside of this machine apparatus. You can do it in the head of the machine as well with ultrasonic or UV or quartz type heaters.
Okay.
The faster processes, by the way, which I've run out of time to go over with you, really is the thermoplastic processes, and that's from page 31 on. It kind of jumps into the different thermoplastic processes. It even explains how the pre-consolidated sheets are made. And these are the fastest processes available right now. We can cycle, like I say, 5 minutes to 45 seconds. There's a whole bunch of different processes described in here, and I'll just blow through this really, really quick. These are 2 of our presses. They're not our only presses, but these are 2 of our presses that are vertical. This system right here is about a $750,000 system, and it actually can mold large parts with undercuts. The machine is, both of these presses are 12.5 feet tall. There's another thermoplastic process behind the one that does continuous pre-consolidated sheets that wants to be a continuous thickness. There's also something called thermoplastic hybrid injection molding, okay? And this is where you take a pre-consolidated sheet, and it's kind of hard to understand what's going on in this, but this isn't an, shoot, sorry. This right here.
Hey, Alan, I think we're at, Alan, hold on. I think we're at a point where we can be kind of talking next steps on.
Okay.
So if you were to sum up kind of the ones that you think have the most promise for small run,
yeah.
So small run prototypes, and then definitely the confines within our competition, we're looking for things like the lowest cost entry, things that are scalable on a global level. If you had to pick one of these processes, if we were going to approach you kind of to involve ourselves in more of a let's get started webinar, which of those would you pick, and then what would you like to do for a next overview?
Well, yeah, the thermoplastic process. Thermoplastic process and the quasi-isotropic process, which is described right here, shows that this literally shows, if you just scroll through this presentation, it'll show how you can see, from the point you load material, it compresses, the mold's heated, it cures, the mold opens, and then parts ejected. This type of process is probably going to be the most conducive, I think, in general for the UAV market. It's flowable, so you can have huge variations in thickness. The tooling can be done reasonably inexpensive, and by that, give you an example. We can tool up a small 32-inch long UAV, let's say. Everything, all the entire fuselage, the booms, the tail sections, the kind of thing like you saw in our brochure, for probably in the neighborhood of around $35,000. The tooling, we could get 5,000 shots out of that tooling, and we can cycle it every 10 minutes, and in some cases as little as 5 minutes. The thermoplastic tooling can potentially be even a little less, but the geometry is a little more constrained. You have to have, it wants to be more of a continuous thickness and accomplish the variations in thickness with ancillary components. This right here is one of our presses that is 225-ton capability. It's a 28,000-pound press, and this is a 36 kW oil heater next to it. We oil heat the platens. The molds are very simple. They're straight pull. They're aluminum, so they're reasonably inexpensive. We produce them all in-house. And just so you all understand, I mean, we will help. For this cause, conservation of flora and fauna is very dear to my heart. And we are actually our facility sits on a nature preserve site. Ourselves that we self-fund, and we have rescued crocodilians on our property here. We have a Nile crocodile, a Siamese crocodile, and an American alligator and giant tortoises on this property, all of which are rescues that were confiscated by our Fish and Wildlife in the state of Florida. So, we're very keen to help any way we can, and we will make costs of everything that anything that we do, anything we're in control of and we can help with, we'll make them as painless as possible if you were to want to work with us on the development of your products. So I'll make that offer to you, and I'm also happy to this is not a business thing for us at all in this situation. This is really about the conservation side of it. So anything we can do, even if that is to point you in the right direction and you go elsewhere and do it, we're happy to help you do that, and in pursuit of the cost. So there's a lot of stuff I didn't really get to talk about that we can go over another time. Like we do pin fins that are heat sinks. You can thread in anywhere that you need a heat sink. That's one of our new patented technologies. There's more descriptive data in here on co-laminating the metal and also the dielectric stuff. And Princess Aaliyah, you're welcome to send this out to anybody that is interested in having this document, and they can. I think if they go through it on their own, chances are everyone's going to come up with a lot more questions along the way.
Yeah,
That'd be a really good way to go. Like, I guess what I'm envisioning, if we could get that thing, there's definitely some specific applications I think a couple of our teams are looking at doing. Some of us are using more or less the same design, so that process you just mentioned might be interesting for those ones if we were to band together to do a run. Definitely would be interesting to see some of those more maybe slower but less quantitative techniques. The ones that are really more one-off techniques. That'd be interesting to know more on. But let's do that. If you could send that document to us, we'll push it out to everyone on this webinar. We'll kind of assemble a series of things of what we'd like to follow up with you with on, and we maybe go from there.
I sent it to Princess Aaliyah last night.
Okay.
So,
Right.
I would have to say I met Alan at the AUVSI conference in May, and I was really intrigued by his tricopter and the fact that it's waterproof. Of course, it makes it very unique, but the ability of it to fly for about 40 minutes, is that the time frame on that? I think 35, 40 minutes.
Right.
So that was what kind of attracted us to his booth. But then as I started talking to Alan, and his passion about wildlife and conservation and all the work he's done made a lot of sense. So what did you say this was supposed to look like? Because everybody comes up with some other. Mike, what would you say that looks like to you if you saw it for the first time?
That
Yeah.
looks like a mold, and that's the microps. I always screw that thing up. It's a highly zoomed in version of the material. I'm looking at grain structure. I have a mechanical engineering background. I'm just forgetting the name of it. I mean, it doesn't look like anything to me. It just looks like grains.
Grains?
Grains, like for material, like using
Okay.
microscopy. Is that the right word?
This is a just to give you an idea of what we're doing with this structure here.
Oh, you're looking at. I'm sorry. I was looking at the slide.
Oh.
No, I'm sorry.
Okay, I'm
Oh,
sorry.
sorry. Yeah, go to
I don't see the grains.
go to the video there. So this this right here, the process that I have up on the presentation right now, that quasi-isotropic discontinuous process, where it shows you there, you load a charge, you close the mold, you heat the mold, you charge the flow, it disperses in the tool, and then you have a cured part. That's what we're using for the bulk of this UAV structure in the tooling process. Okay, this just to give you an idea how we did this design, it's quite unique. And it might be something, some good food for thought for everybody on how to build, some UAVs in the future. We're molding this top cap right here, the top cap of this fuselage. I'll try to show you a little better here on the video camera what that looks like. Sorry, there we go. There we go. Get it all in the camera. So anyway, that top cap, we're molding one piece. Then the tail section, this tail section right here, which is kind of a conventional tail with a nacelle, with a swash plate in it right here, we're molding this tail section in two halves, okay, that come together, and they get joined at a parting area. So they get bonded together into two pieces. Then those two pieces then get joined to the upper cap. And then there's one single chassis that all of the electronics sit on that's held in to the underside of this top cap, which is made out of a glass material, so it's radiolucent, allowing antennas to emit. That is screwed into the underside, and with only two screws. So it's very, very simple assembly, and it can be static isolated, so for shock and vibration. And then there's so in other words, this top cap and the tail section get joined into one monocoque. That is my McLaren tub, if you will, okay? And then the bottom hull here is just it's nothing more than a fairing that happens to be waterproof with a waterproof parting gasket all the way around the perimeter of it that seals it up, watertight. So we even put a Picatinny rail on the bottom of this thing, so you can mount some nice implements like a machine gun or a taser or something friendly like that.
You mean a GoPro camera?
or a GoPro camera, I suppose. And there's two sensors right here that are actually behind those windows. So, this thing floats. So there's a pontoon here at the tail, right down at to give it a little bit of buoyancy there. And even our nacelles are waterproof. They're aerodynamic and they're waterproof. So there's a heat sink integrated into the nacelle, in fact. And just with a single button, you can articulate the booms back into a back into a flush position parallel to the hull.
That's a neat little design.
So it's designed to be able to. It does not require a transit case. The materials that we're using are extremely rugged, so you can actually shoulder sling it. You can see I actually have a sling attachment right here, and there's another one that goes right up at the nose of it, right up the bow. So this allows you to literally hang it just like so over your shoulder. And very easy to deploy and fold out the booms. So,
cool.
So this entire structure will get molded in 10 minutes using the process that was up on the screen.
Cool. That's neat.
So,
well, Alan, I wish we had more time to talk about that guy. That looks awesome. We're actually, a lot of us, we got to pop onto our next kind of calls during the day here, but let's keep that. So for everyone else on the call here, for the kind of you guys still on, take a look at those different processes and kind of what, based on what Alan's just said here, let us know if you want to go another direction. Maybe we can schedule another time with Alan to kind of go next steps on this stuff. Alan, thank you so much for taking the time to show off both your drone and then give us an educational background on all the various processes that your business are involved in. Really appreciate the time.
no
Yes.
problem.
Thanks, Alan. That was really great. I think you did such a great job. We didn't have questions today, which is surprising because normally we do. There is one question for that drone, though. Mike, do you see it?
Well, yeah. Alan, are you gonna sell that drone?
We are. We're in the process of making some fairly significant enhancements to it, and basically completing the tooling process on it. And yes, it will be for sale. And we're very much a behind-the-scenes company, so we're looking for literally anybody that would be interested in taking this and packaging their electronics and sensor payload into it. And we're really open to any business relationship. We do as much or as little as any of our customers want. Sometimes it's to just make a prototype, and sometimes they hire us to do everything. So, we're open to just selling the fuselage and the motor, basically the fuselage with motors, and you can populate it with your own electronics and build out the guts of it, or we'll be happy to do a fully integrated solution if you want it. So we're open to any scenario, and we're looking for partners on it, and people with their own unique applications, and we're happy to be a behind-the-scenes supplier. That's typically what we always are.
Okay, well, thank you so much, Alan. Appreciate it again, and we'll schedule a part 2 because I think you have some really, really important, useful information for people that are interested in learning more in depth about the processes and the behind-the-scenes work. So thanks again, Mike. Anything on your end?
No.
How's your
See you
team
guys
going?
Later, guys.
Thank you all very much.
Bye.
Take care.
Bye.
Bye.